Hello everyone, how are you? I hope that you must be enjoying the lecture series. In my earlier lecture, I told you what are the various types of beams and what are the various types of reactions and the external loads that are acting on the beam. Now, we are in a position now to draw the beam and its free body diagram. And with the help of the external loading, we will be trying to draw its free body diagram and the shear force diagram and bending moment diagram. You must always try to relate whatever we are studying with our common life. Just to give you an example, I taught you cantilever beam. And in that cantilever beam, you can see in the home also, everywhere you use a cantilever beam. Suppose I tell you to hold a stick in your hand, then if you hold at one of the end and the other end is free and you are holding the one of the end tightly, then it becomes a cantilever beam. So there are various examples that we will be relating in our, you will be able to relate whatever we are studying with the things around you. I just gave you example. Another thing which you can do is a very common practical thing, that whenever you are writing with your pen, then try to see how you are holding that pen, how that pen is being supported in your hand. So it will be very interesting if after studying this lecture, try to draw what I am teaching you, the free body diagram of the beam, and I'm telling you to draw the shear force diagram and bending moment diagram. Just try to draw the SFD and BMD of the pen you are holding in your hand. So I am just giving this question to you because this recently appeared in one of the very prestigious organization, a very important interview question. And after relating this, everything what you study in this chapter, after relating this with the physical thing which is happening with the pen, I think you will be able to draw correctly the shear force and bending moment diagram of the pen. Like I just gave you an example, you can see many examples around you where you will see that you will be able to check it out, what are the various types of loads that are acting on the beam or the component you are studying. So dear friends, to make your mechanical engineering very interesting, try to relate each and everything that you are studying with the physical scenario. So it was just to make this topic interesting, and minded, this is very, very important topic. You cannot leave this topic out because this is just the basis that I am creating in studies of deflection of beam that we will be covering in the later module. So coming to our topic of discussion, we had already discussed the types of load that are acting on the beam. So moving on to the next, I just told you earlier also, whenever you want to see what are the types of forces that are developed in the beam upon external loading, what you have to do is to cut the section and check it out. What are the internal forces or the reactions that are being developed due to the external load? So this external load will be the only factor which will result in the internal reactions, and you can see that internal reaction only after cutting the member. Suppose I say that this is my member, and I have applied a load P and it is being supported at the two ends. I just give you a question. Suppose I cut this member here. X is my section plane, that is the cutting plane. If I cut this member here and I tell you to what are the internal reactions or the internal resisting forces what are being developed in the beam, then what you have to do is just cut that section out and see what are the reactive forces that should come in picture to make the beam in equilibrium position. If you are able to visualize, again and again I am repeating the term equilibrium, and that also static equilibrium, you will not face any difficulty, mind it. You will not face any difficulty. So keep this subject a matter of interest always, and always try to relate this thing. Whatever we are studying, dear friends, whatever we are studying here, it is a physical phenomena only. That is in actual practice. That happens actually. So just coming back to my lecture, that is the internal reactions on the beam. So whenever you cut the beam, any section you have cut the beam, there are always three possible types of internal reactions that you will be getting. So to keep that body in equilibrium, the reaction is coming into picture. And what are the types of reactions that are coming is, one is the normal force, the other is shear force, and the third one is bending moment. Every internal reaction that we will be studying will be moving around in this topic only. This three internal reactions only. You will be seeing that whenever I am talking about the word reaction, then I will be putting these three forces only, so that our member is in equilibrium, and then again we will do the further analysis. So I've just showed you a arbitrary, suppose this was my arbitrary body. This was my arbitrary body, and I have cut it out here. I have cut it out here, and I am trying to look at what are the types of forces that are being present. So just to give you an insight to what are the types of reaction that will be developing in the member, just you can see that here a twisting moment has been shown as T. This is also known as torsional moment. Why torsional? Because in the shaft, when you twist or give a moment in the plane that is parallel to the cross section, then you will be getting a twisting moment, which is also known as torsional moment. The other is the normal force that will be getting. This normal force will be always perpendicular to the section you have cut. Suppose I have cut my section. This is my section cut. I am hatching it out, and the normal to this section will be the normal force. And similarly, the shear force is always tangential to the section you are cutting. So this was my section, and you can see that this V is nothing but the shear force. This is the shear force, and this is acting parallel to the section you have cut. It is always parallel. So just make it a thumb rule. Always the normal reaction, that is the normal force. The normal word represents the force which is perpendicular to the section, and the shear force is also termed as the tangential force, and this tangential force will be the shear force only. And the other reaction that can appear is the bending moment. And the effect of all this internal reaction will be to bring the body in a static equilibrium condition. So we are seeing that components which are found perpendicular and parallel to the section plane are nothing but the normal and shear stresses developed. And also sometimes you will be finding that a moment is also developed at the reaction. It will depend on the type of external loading. It will depend how the beam is externally loaded. We will see in our various examples. I will take many problems, dear friends, and you will never find difficulty in tackling a new problem that might be appearing in your examination. So coming on to the next is the free body diagram of the reaction after cutting a section. Just don't get afraid by what is the loading condition and what is this P1, P2 and W. Don't worry about this. I will be talking separately the nature of these forces. Just to draw the free body diagram, just to teach you how I will be drawing the free body diagram, I have taken a general case. This is a general case. It is not a part of the problem. It is a theory only. And you can see that there are two concentrated loads. This is P1 and the concentrated load is P2. And these two forces are also along with a uniformly, this load is a uniformly distributed load. But this force is not entirely distributed in the whole beam. As you can see, a part of patch, that is the red patch. This is the red patch, and this red patch is present at a part of the beam only. Suppose I take this as a distance A, then only distance A is having the uniformly distributed load, and other span is empty. Like this span is empty. So there are three types of forces present. there are three types of forces means there is P1 and P2. This both P1 and P2 is a type of concentrated load, and the W is signifying the loading intensity. They always, I had told you earlier also, whenever we will be talking about uniformly distributed load or uniformly varying load, then we will be assigning with a loading intensity. So dear friends, this is W is nothing but loading intensity. This is loading intensity, which has the units of Newton per meter of length. If the length is taken in meter, then it will be Newton per meter, or if the length is taken in millimeter, it will be Newton per millimeter. So it will be according to the units only. And you have the two reactions here, that is A and B. And again, this type, again, this is reaction A is, if this triangular shape is present and it is supported at a point, then you can infer that this reaction is nothing but a hinge joint. And reaction B, as you can see, the tiny balls which are present beneath this section B is a roller support. So at the one end you have hinge, and at the other end you have roller support. And mind it, I had already told you earlier that whenever there is a hinge, then it will never afford any resistance to the bending moment. And also in roller support you have reaction in only one direction, because in the other direction it is free to move because of the effect of thermal expansion. So I will be taking section at 2 points, and I will show you how the internal forces are coming into picture. As from the last slide, you just saw how an arbitrary body, if it is cut and it was loaded earlier. So this was the internal forces that I showed you for a arbitrary body. So in the same manner, I will be taking two different sections, and I will show you how the internal forces are being developed in the two cases, in the two sections that I will be taking. So here, what I have done is, I have taken a section after the load. Means here was the point C. As you can see that I have drawn a red line here. So this is my section plane. So this is my section plane, and I am cutting my beam in this manner such that it is cut perpendicular to the longitudinal axis, and it is passing through the point B. So this point, the line passing through the point C is nothing but the section plane. So I have cut it out. This was my section plane that is still shown here, and I will be showing you what are the internal forces that will be coming into picture. So dear friends, this was always the external reaction that will be coming because of these loads. In the hinge A will be always upward. Why upward? Because to balance these downward forces, upward force should come into picture. So again, mind it, this RA is nothing but the external reaction. It is not the internal reaction, dear friends. It is the external reaction. It is always the external reaction, because the hinge is outside this beam. Hinge is not, it is not inside, or it is not the intricate part of the beam. So it is the external reaction. It is the external reaction. And what I have showed here, these things are internal reactions. So never get confused. Always the external reaction that will be provided by the hinge will be in such a direction that it will always be in the opposite direction to the applied load. As you can see that the P1, P2 and the UDL in the patch of a beam are all acting downwards, then the reaction from the hinge will be offered to the beam in the opposite direction, that will be upward only. So the internal reactions which are developed in the beam are the shear force and the moment. So why moment and why shear force? That must be the question. And why not the twisting moment? Because I told you the three types of internal reactions that we will be getting is the normal force, the moment, and also the torsional moment you can get, and the shear force. So all four types of internal reaction you are prone to get. But in our case, as there are no any moment parallel to the section of the beam, so we can conclude that there will be no internal torsional reaction. Would the beam would have been suffering, just I will be showing, if the beam would have been suffering a moment, suppose T moment, then the reaction would have developed in the beam. So just I am deleting this for the sake of clarity. I am just erasing it out. So here only what type of internal reactions that you are able to see is One is the moment and other is the shear force. So the internal reactions developed is moment and shear force, So why is this coming into picture? You can see, friends, just as I have cut this section. Now, after cutting, just remove everything. Just means you just cut the beam and move from that point. So what will happen? This beam, that cut part, this cut part AC section will try to get rotated about A point, because A is hinged, A cannot move. So about this point A, this beam will try to get rotated. It means that a moment must be present, because the hinge cannot restrict the bending moment. So a reaction moment must come into picture such that the hinge is not allowed to fall down. And this is the concept always we use in our analysis of free body diagram. Just I'm giving you example from the mechanics. Just I'm deleting the ink here, and I'm just giving you a simple analogy that you can draw from the mechanics. Suppose this is my string which is holding a mass of mkg. So this is simple mechanics that you would have studied in your 11th and 12th. Just I am drawing an analogy here so that you can compare here. So here again, whenever we used to draw the free body diagram, the first step we did was to cut this spring. So whenever you are cutting this spring, just I'm showing in another egg, whenever you are cutting that spring, what will happen is the mass M will try to fall down. Why it will try to fall down? Because mg load is always acting due to the gravitational pull of the earth. So gravity is always trying to attract this block. Come on, block, come to me. So this is the gravitational force mg. Now if I draw the free body diagram, then how I will draw? I will take this mass, block of mass m. I will draw the mg force. That is the external force. Like here we have the external force as the loading on the member. Like that only, this mg force is nothing but an external force that the gravity is applying on the body to pull it towards itself. Now after you have cut the string here, then the block will try to come down. So to prevent the block from coming down, always what you have to do is to apply a force which is opposite to this mg load. And this opposite force is nothing but the tension force. So again, I just want to remind you, this tension is again an internal force. So whenever you are cutting a member or you are cutting a section, then only you will be able to see the internal forces and the reactions developed in the member due to the external load. So now again, I will try to draw the free body diagram of the support. So here was the support. This was the support. I have drawn the FBD of block. Now I will be drawing the FBD of support. So this was my support, dear friends. This was my support. And to keep this member in equilibrium, so reaction of T will come here. As I was showing you, whenever I was teaching you how we will be balancing a bar which is subjected to a multiple axial loads, there we saw that the force which was acting towards right in a member, and that member, if it is attached to the second member, so in second member the reaction of the first member will come into picture, and the force will be in the opposite direction to what it was in the previous member. So this always action reaction pair, you will have to think it, and it will keep on going in each and every analysis. So this tension and this tension. So what was the situation when you have not cut the spring? Then what was the situation was this T and T you were not able to see, because this was the internal reaction. So this internal reactions you will be able to see only in one condition, that after you have cut the member. On cutting the member, the internal reactions will come into picture. So here just I'm coming back to my topic. Just I was trying to draw the analogy. Here also a shear force and moment is coming into picture. I will take another section and I will show you how the internal reactions will be coming, internal forces will be coming in the other section. Like I have taken this section. See, this section is taken from the right hand side. Means I have this was my part AC. This was my complete beam, and this was my complete beam. So So this beam I have divided into two parts, that is AC and CB, AC and CB, and I will be drawing the free body diagram, or I will be showing you the internal reactions from the right hand side. So this was from the left hand side, that is AC part, and here it is the BC part. Now you will be able to see that whatever I drew for the section C by taking it from the left, the same reaction, the reaction of that internal force should be in opposite direction at the same plane section C if I take it from the right hand side. It means that if certain section has been taken and if you have drawn a force upward, it will become downward due to the reaction effect, and if the moment would have been clockwise, then it will come out to be anti-clockwise. Always the reaction will be in the opposite manner. So in this case, in our case, as you can see here, the shear force was in downward direction and moment was towards, that is in ACW, anti-clockwise direction. So in the reaction of CB part, this AC part here we have shown, and in CB part we will be seeing that the shear force will be acting in the upward direction and the moment will be in the clockwise direction. So here you can see this moment M dash is in the clockwise direction and the shear force B dash is in upward direction. So friends, we will be trying to draw our internal reaction by cutting the segments like this only. This will be the situation. Now I just want to remind you of the sign convention again, because I had taught earlier also, but I just want to recall you that this situation where you are seeing that, if I have taken a section and this is acting in downward direction here, and the moment is acting as a sagging moment, because this is trying to make the beam of this shape. This is trying to make the beam of sagging shape, means the beam is happy, so it is a sagging moment and it is taken as positive. But here again you will be able to see that in this section again this moment is trying to make the beam sagging in nature, so it is again a positive. So whatever case you will take, that then the moment is coming out to be sagging and it is taken as positive. So whenever you are getting the internal reaction in this scenario, like exactly like this, that the beam is sagging and the shear force here is in the downward direction, here it is in the upward direction, then what we will conclude that this is a case of our positive bending moment as well as the positive shear force. So here you can see this is the case of a positive shear and positive bending moment. Don't get confused by the convention which I had taught you that in clockwise direction our shear is positive. That is true whenever we are taking the element of the beam. Suppose I have taken an element of the beam, I have taken just an element of the beam, and in that case if the shear is acting in clockwise direction, then only we take it as to be positive. But here what is the case is, this is also a clockwise only. If I just take a section here, then again a shear force will be developing in upward direction and this system will come out to be in clockwise direction only. So don't get confused by this, and here sagging moment you can easily see. So this shear force I have the convention which I had taught you will be clearly, you will be visualizing here. What is happening here is this was the internal force and the effect of external forces that we are seeing. This was the positive shear because this was the internal force, and internal forces are always opposite to the external loading. Here also, due to the external load, this beam is trying to go down and this is trying to go up, means a clockwise type about this plane. This was the plane which I was talking here. About this plane, it is making a clockwise rotation, and whenever it is a clockwise rotation due to the shear force V, external shear force V, then we call it as the case of a positive shear. So positive bending moment is when it is sagging, and positive shear is when the external load is trying to shear off the member in clockwise direction. So this is the complete effect, that is the sagging moment which is being produced, which is taken as positive. If it would have been like this, that is the hogging, then it would have been negative. Just I'm rushing here because I have already discussed with you all. Now I will be directly coming to the first problem. This is not a problem also, just a part of theory in itself. just I will start or introduce the drawing of shear force and bending moment diagram. So this SFD I will be writing now, and then it is shear force diagram, and this bending BMD is nothing but bending moment diagram. So for the first most simple case is a cantilever beam which is loaded at one end. You can see here, friends, this is a fixed end. This is a fixed end, and you are applying a point load in the free end. This is the free end. So it is a beam. I will never be using the type of beam in my question. I will not be writing, because it is up to you to identify, to analyze what type of beam you are studying, so that it will be very easy for you to draw the reaction in the beam. So this is a type of a cantilever beam, because one end is fixed. One end is fixed. Now, if one end is fixed, then we always know what type of reaction will be coming. As I had already told you, that in the case of a cantilever beam, or in the case of a fixed support, you are always, you will be getting is one bending reaction. Why bending reaction? Because the fixed part always offer resistance to bending moment, external bending moment, and also a force will be directed in such a direction that it will be opposing the external load. So I will be just in the solution part, I will first be drawing the free body diagram. So what is the first step to draw the free body diagram is to remove all the external supports that the beam is having. Like in our case, this was the fixed support and this was the point load. So first of all, I have to remove this part. So I will be removing this part here, and I will be drawing the free body diagram. The word free itself means that the body is free of any external supports and free of any external arrangement which is supporting that load. So I will be drawing here. Just I have taken this member. I have isolated this fixed support. I have isolated it, and I will be taking here. Just I'm changing the color for convenience. So this was my external load P. So the force P, if I don't have support here, just recall how I taught you the free body diagram of a string. I told you about the beam. Whenever I am cutting the beam, it is trying to rotate in itself. So what will happen is, if I don't have this fixed support, what will happen is the beam will come down. The wave beam will be rotating like this. So to prevent this beam from getting rotated, you have to apply a moment in the opposite direction to this external moment. So this external moment is trying to rotate the beam in the clockwise direction. So you must have a reaction such that it is acting in a counterclockwise direction, so that it is restricting the effect of the external load. So one reaction you have got, that is the moment, and other reaction will be obviously a force which is opposing this P, and I'm denoting it as R. So the two reactions which are coming into picture is reaction R and moment M, which is acting. This moment M is acting as this was the clockwise moment, and this was the, this will be in this direction, so it will be anti-clockwise moment, that is counterclockwise direction. So it will be counterclockwise because this was clockwise, so it will be opposing this, and this reaction will be coming which will be opposite to the external load. So this moment is in counterclockwise, or you can say it as anti-clockwise, and this reaction, external reaction, so a moment and a vertical reaction is coming from the fixed support. So this fixed support is offering a moment and the vertical reaction to balance this beam. So now I will be constructing the shear force diagram. How I will be constructing the shear force diagram? Just you can see I am erasing everything here, and I will be showing you how I will be drawing the shear force diagram. So suppose this was my fixed beam. This was my fixed beam, and I just drew a axis on which I will be drawing the shear force diagram. So the free body diagram of this was, just I am drawing my free body diagram in this part itself, just by changing the color. So this was my P, the reaction P, which will be P only, RV equal to P, that is R, that is the vertical reaction is nothing but P. I have represented a suffix V here. The V represents the vertical term. So this P is nothing but V, and a moment will come into picture, that is P into L. Suppose the length of this beam is L, so it will be P into L. So how I will be constructing my shear force diagram? Just do you remember the sign convention that I told you? Whenever the shear force is trying to rotate the member in clockwise direction, then we will be taking it as positive. So see this force, that the reaction force is trying to rotate this beam. This is having the sense of clockwise, so it will be positive. One more trick, just for fast calculation or fast drawing of the diagram, I will just teach you is LURD. So whenever in left direction, in the left hand side, you have upward reaction, it will be positive. And in the right hand side, if you have downward reaction, it will be negative. So it just you can treat it as a trick only, that in left hand side upwards denotes positive, and right hand side downwards represents negative. So this P force, as you can see, is in the leftward direction, and it is acting in upward sense, so it will be positive only. So I will just draw a magnitude of force P here. So as no loads or no concentrated loads are acting between this point and P point, so this P force will be constant over the beam. So this will be constant. It will be straight line. It will be a perfectly straight line here. So it will be P, and again, as this is a downward force which is acting, and downward in the right hand side right hand side downward is again positive. So this is downward side it is acting. So I will put here a downward reaction force, that is of magnitude P itself. So here the shear force will come out to be 0. So don't get confused when someone asks you what is the shear force at the free end, then it will be it was P, and due to the effect of external load P in the downward direction, it has come out to be 0. So don't get confused whenever someone will try to confuse you what is the shear force at point, that is the free end. So this is the shear force diagram, and it is always positive because it is above my reference line. So it is above my reference line. So the trick was that in the left hand side, if the force is upward, I will be starting with positive. In the right hand side, if it is downward, then also it will be positive only. It will be positive only. So I will just try to draw this diagram from left hand side. So suppose I have a reference taken here, and I am trying to draw the diagram from right hand side. So again, this P force is in downward direction. So in downward direction, in the right hand side downward, it is positive only. So I will take it as positive here. P. Again, I will have a constant here. In the left hand side, it is again in upward direction. So it will be like this. So the arrow, I am drawing it opposite here, just to make sense that it is positive only. So whenever you have shear force in the left hand side and it is upward, it is positive, and in right hand side, if it is downward, then it is positive. We will see how these things are manipulated, because don't get confused here that the reaction forces are being drawn here, and whenever there is a concentrated point load, then we are taking the effect of that also. Like here in the vertical reaction, the reaction was equal to P, as there was no any other force, so we could have equated in a static equilibrium condition that this R plus minus of P. Why minus? Because it was acting in downward direction, is equal to 0. So we have got R equal to P. So here directly I have written, because now you would have understood how we are taking the static equilibrium equation. So now to make your the drawing very easy and to drawing very fast, so you have to take the calculation like this only. Whenever you are seeing the vertical forces, then the reactions will be equal to that only. Or if there are 2 or 3 vertical loads that are present, then the reaction will be the summation of that will be in the opposite direction. Now moving on to the next, we will just see how it is drawn. This is my final answer, and here you can see that always a positive shear force is acting in the beam, and what is the magnitude is F only, that is equal to external load which I showed you earlier, which is nothing but P. So in the question itself you can see here F force was acting, so shear force will be constant throughout this beam. So remember dear friends, whenever a cantilever beam is subjected to a point load at its free end, then a constant shear force is developed throughout this beam, and the magnitude is that of the external force, that is F. This L by 4 and L by 4 section, it has been taken just to for the basic understanding that in each and every section that you will be getting, the shear force will be of same magnitude, that is F only. And this negative direction, you are not seeing this yellow patch, it means that the shear force is lying above the reference line and it is always positive. In the similar fashion, we will be trying to draw the bending moment diagram. So this is the bending moment diagram that I have directly shown you. So I will be just drawing with the help of the equation. Again, I will draw my beam. I will draw my beam and I will come up to this solution how I have drawn the bending moment diagram. So this was my external force F or P, you can say anything. This was the F, and I am trying to take a section. I am taking a section X here, which is at a distance of X from the free end. So I have taken a section X which is at a distance of X from the free end, and I will try to write what is the equation at this section of bending moment. So if I represent the bending moment at section X as mx, so this mx will be nothing but F into X, and as this F force is trying to sag the beam, so it will be always negative. So mind you dear friends, that sign convention is going to play a vital role. So don't make mistakes in the sign convention. So here this sagging moment is producing a negative moment. So this Fx will be a negative only and it will be acting in the downward direction. So just at the free end itself, the value of X is 0. So here X is 0 and here X is equal to L. So what is the maximum bending moment that you will be getting is at the fixed end. So M at the fixed end is nothing but minus F into L. So this is the moment that is acting at the fixed end. So whenever you will draw, now we are in a position to draw the bending moment diagram. So come to the mathematics part. Whenever you have a line y equal to mx, then that line is, so y equal to mx is a straight line which is passing through origin and it is making a slope of m units from the positive x-axis. In the similar fashion, if you consider our origin to be at this position, because I am measuring x from x equal to 0 and I am going towards left, and my slope is minus, what is the magnitude of the slope that I have? That is mx equal to minus f into x, and our slope is minus f. And as you had seen earlier that the shear force is remaining constant throughout this beam, again we can make a very, very important conclusion here itself, that the slope of the bending moment diagram will give me the force. So this is the slope of the bending moment diagram, and it will give me the slope. So just I want to represent this thing mathematically, that dm by dx, which is nothing but the slope of the equation of m that we will be drawing the bending moment diagram, is nothing but the shear force V. So shear force V is the slope of bending moment diagram. Now we will try to draw a straight line from this point, as we have considered our origin here, and we will be getting the bending moment diagram. So this was the reference line that we had drawn earlier. This is the origin, and this is the length up to which we have to draw it. That is up to length L. So from x equal to 0 to x equal to L, we have to draw the bending moment diagram. So at x equal to 0, if you put in this equation, I'm just writing my equation again, mx equal to minus of f into x and f into x. Then if I put x equal to 0, then moment is 0. So my point will start from here only. So here, from here only, my diagram will start. So at x equal to 0, it is 0, and the slope is remaining constant, and the slope, magnitude of slope was minus f. So it was the negative slope which I was getting. So here, as I will be drawing as the beam is hogging. So I have taken the negative sign. So I will be drawing my bending moment diagram below the reference line. So below the reference line, the diagram will represent my negative bending moment. So at x equal to 0, if I put here 0, then mx at x equal to 0 is 0. So that point will be coming on the origin itself. Now I am writing the equation. I am writing the equation here again. So it is mx equal to minus of f into x. So at x equal to 0, mx is 0, and at x equal to L, mx will be f into L, and this will be the maximum bending moment in this entire cantilever beam. So suppose this is my cantilever beam, and I am drawing my bending moment diagram. At x equal to 0, it is 0, and at x equal to L, it is f into L, that is FL. Now I will be joining it with the help of a straight line. This is a straight line. You can see the similar diagram here also. Here a straight line is you can look at very carefully, and it is very much negligible that it is a straight line, and you know that a straight line has got a constant slope. So I can conclude in the reverse manner that the beam is suffering a constant shear force, and a constant shear force will only come into picture when there is only one concentrated load acting in the cantilever beam at the free end. So if many a times it is negative, many a times the question will be given to you, like they will be giving the bending moment diagram, and you have to infer the result. Means you have to do the backward calculation, and you have to arrive at the loading condition of the beam. It means that when you are given the bending moment diagram, and with the help of the bending moment diagram, you have to find out the shear force diagram, and with the help of shear force diagram, you will be arriving at the loading condition of the beam. So I will just show you how you can proceed in a reverse manner. So you can proceed in a reverse manner, like you can do is, suppose this is my bending moment diagram given into question. This is my question itself, and I have to arrive at the result, that what is the loading condition of my beam. Now, first of all, the first and important observation that you have to make is, you have to see what is the end condition of the bending moment diagram. I mean to say is, here you can see that bending moment is not equal to 0, and here bending moment is 0. So first conclusion that I will make from here is, one of the end of the beam is either fixed, or a concentrated moment is acting at that point. So what are the conclusions that I can make if the shear force if the bending moment diagram has non-zero bending moment at the end? Then the conclusion that I can draw is, either the end is fixed, or there is concentrated moment at the end. Now, out of these two conclusions, how I will cancel one conclusion, you can see here. Like here, you can see that this is a straight line. This must also be given in the question, that it is a straight line. And as a straight line has a constant slope, like the general form of the straight line is y equal to mx plus c, and this m is nothing but the slope of the line, and always for the straight line, this slope is always constant. Now, as this has got a constant slope, so I will find the slope from this diagram. I will find the slope. So how to find the slope? Slope is nothing but change in y with respect to change in x. So what is the change in y? This is my 0 point. Change in y is FL. Change in y is FL, and total length is L. So what is the shear force? That is what is the slope that I am getting is F. It means that at each and every point, suppose I don't take the end point, I find a slope here. I find a slope at this point. So what is the slope at this point? What is the slope at this point? It will be moment at this point, that is nothing but FL by 2, FL by 2 divided by L by 2, and again I am getting F. So at each and every point you are getting a constant shear force. Now if I am given to draw the shear force diagram by looking at the bending moment diagram, then I can simply say that my shear force diagram is constant throughout, and it is having a magnitude of F always. Now from this shear force diagram, this is nothing but I am writing here in short, that is SFD, I will be drawing the loading diagram. So there are three types of diagram. One is the loading diagram, which is showing how the beam is externally loaded by the forces, and the second is shear force diagram, and the third is bending moment diagram. So these three goes in sequence, and if you are drawing the diagram in the reverse manner, then you have to first draw the bending moment diagram, then shear force diagram, then again the loading diagram, and with the help of which we will be able to know what is the external loading on the beam. Now here F is acting in upward manner. So just I will draw a line which will represent my beam. This is my beam which I have just showed by a straight line. And as F force is acting in upward manner, so I will go with my formula, that is LURD. Left upward is positive, so it is positive and it is acting in upward manner. So here reaction force will also be in upward manner. And now as the bending moment at the free end is 0 and at the fixed end is FL, that is maximum, so I can conclude that there must be a force which must be acting, means the bending moment at the point at which the force is acting is always 0, because the distance of that point, as the line of action of the force is passing through that point itself, so the bending moment is force into perpendicular distance is 0, so the moment will also be 0. It means that a force must be acting at this point, and as there is a moment at the end, so it must be a fixed end. So this must be a fixed end. So I have arrived at the result taking the conclusions from the backward side. So here, as I told you, that there can be another conclusion, that there is a concentrated moment at the end. So this result can be discarded on the basis that if there would have been a concentrated moment at the end, then there would have been a sudden jump in the bending moment diagram. But as you can see that this bending moment diagram is going smoothly, means it is a straight line. It is a straight line. So it is not a case of concentrated bending moment, and this conclusion is void in itself. It is a void conclusion. So this was I explained this one in much detail, because in the later part this will be you will be finding it very easy to do it in the questions that will be coming with different loading diagrams. It will be much easier. Now coming on to the next, as I have showed you the SFD and BMD of a cantilever beam which is suffering a point load at the free end. Now I will take again a beam. Now again I have not mentioned here the type of beam, but you have to conclude by seeing here the fixed end that it is a cantilever beam again. Now in this cantilever beam, there is not a point load here. What is given is a concentrated moment at the free end. As now you can recall the types of loads that we studied, that we can provide a concentrated moment also at the free end. So this is a concentrated moment at the free end, and and you have to draw the shear force diagram and the bending moment diagram. Now, again, the first step that you will be drawing is the free body diagram of the beam. The free body diagram of the beam will be, you have to draw a straight line representing the beam. You have to remove the fixed end that is in the right hand side. Now, if you remove this end, if this you remove the fixed end, then the beam will fall automatically on the basis that there is a concentrated moment at the left end. So to support this, means to support the beam, you have to provide again a concentrated moment in the opposite direction to the applied. So this moment is the external moment applied, and this is the reaction. This is the reaction. Now, in this case, again, if I draw my vertical reaction for the sake of my formalities that I will always draw. Whenever I see a hinge, I will draw the two forces. Whenever I see a fixed support, then I will again draw my three reaction, that is in the vertical direction, in the horizontal direction, and one moment. So moment I have got already as M, that is the reaction itself, because this M will be balanced by this M. So if I represent this as M dash, so M dash is nothing but M here, and here Rx and Ry are not having any external load to give resistance. Means there are no external loads in the vertical and horizontal direction such that Rx and Ry will come into picture. So straight away what we can say is Rx equal to 0 and Ry equal to 0. So this is only the free body diagram of the beam, where at the end only a moment is supporting the entire beam. Now in this case I will show you how I will be drawing the shear force and bending moment diagram. Though it seems to be a very easy question, but a lot of confusions will appear when you solve a lot of problems. Then again, if you try the easier one, then you will see that you are getting stuck. Why? Because if you don't follow the concept, means what is the basis of the drawing of free body diagram and shear force and bending moment diagram, then you will face difficulty. Otherwise, if you follow very sincerely, then I don't think you will have any difficulty in any sort of problem. Now I'm erasing all these things and I'm straight away coming to the shear force diagram. Shear force diagram. So what I will do is, as this was my free body diagram and this was my static equilibrium diagram, that is the free body diagram, and with the help of this diagram I will be proceeding it. Now here, as you can see, that there are no vertical forces, means there are no forces parallel to the cross section of this beam. So if I draw the cross section, suppose I have a rectangular cross section, this is my cross section, as there are no forces parallel to this cross section, then I may conclude that the shear force is 0 everywhere, because there are no vertical forces. This vertical forces is 0, and here also vertical force is 0. It means that if this is my reference line, then my shear force will be coinciding with this reference line. I mean to say is, if this is my reference line which I have drawn, and with the blue ink if I am drawing the shear force, then it will be coinciding with this, because shear force is 0 everywhere in the beam. Now if I draw the bending moment diagram, this is suppose this is my reference, or I am again drawing it. So this is my reference. This is my reference line, and with the respect of the reference line, I will be drawing the bending moment diagram. So this is my reference line. I am drawing the bending moment diagram. You can see from here that this beam, after the application of this load, is trying to hog. So this is a negative bending moment. So this is a negative bending moment. At this end, you just draw the magnitude which is shown here, that is M. This is M. And this M is constant, and in the opposite direction you are getting one M, another M, that is this M. So this is totally negative, and here also magnitude will be M. So the shear force diagram is 0 and the bending moment is constant. Now from this diagram I again want to draw a very important conclusion here, that if the shear force is 0 throughout the beam, it will mean that it is having a constant bending moment. As I mathematically also I showed you earlier that dm by dx is nothing but the shear force, as the bending moment is constant here. So differentiation of any constant with respect to any variable is always zero. It means that shear force is zero throughout the beam. It is a very natural practice just to avoid the calculations that whenever you are drawing the shear force diagram and bending moment diagram, try to draw diagram one after the another. I mean to say that first you draw the question that is being represented. If this is the question, draw its free body diagram, represents all its external load and the reaction, and then beneath that only just you draw a line, a straight line. You just draw a straight line, and beneath that you try to draw the shear force and bending moment diagram, because it will be very easy to analyze in future. So this whole solution I will be showing you again. So this is the shear force diagram. As you can see that this is having a zero magnitude all around. So shear force is always zero for a beam, a cantilever beam, which is having a concentrated moment at the free end. So again, this is the I just told you a few moments ago that we will be drawing one after the another. So this was my beam. This is the shear force diagram, and this is the bending moment diagram. So you will be able to visualize at what distance what is my bending moment or shear force if you draw the diagram one after the another. So this is also one of the simple case of shear force diagram and bending moment diagram. From next lecture onwards, I will be showing you another problem where I will teach you to draw the shear force and bending moment of new varieties of loads. So till then, revise the concept thoroughly and note down all my points, and wherever I have stressed my conclusions that are very, very important, you just try to follow that. Till then, enjoy this subject and have a nice day. Thank you.